Swayam Prabha. Digital India. Educated India.
Welcome to lecture 17, where we are going to talk about plastic design. This is actually a part of second module of Advanced Steel Design course, which is under NPTEL IIT Madras. Before we enter into discussing the plastic design fundamentals and its applications and theories related to the conceptual development of plastic design, let us try to ask a question: what will be the general design considerations in designing a steel structure? Okay, let us ask this question. So, let us talk about design considerations for steel structures. When I say steel structures, I am not talking about conventional structures, I am talking about strategic and special form of structures where the structures resist majority of the load by the geometric form. Okay, I am keeping this in mind because we are always talking about advanced steel design procedures. So, the conventional design of steel structures is not discussed under the purview of this course at all. Okay. So, for example, for our convenience, let us take the design of top side of an offshore platform. Okay, offshore platform is a strategic structure. If it happens to be a compliant structure, it will have a form dominance. Let us talk about the design consideration which you have for top side structures. Okay. So, the first condition should be that the top side members should be designed to have sufficient reserve strength Why it is required? The reserve strength is required to withstand the imposed load during the pre-service life and in service life. So, that becomes my first requirement. The second requirement could be the platform or the structure shall possess optimum safety, reliability, cost effectiveness and flexibility. That is very important. We are talking about form dominance. Okay. The third condition could be the design shall comply with necessary serviceability criteria. That is very important, as stipulated by the design codes. The fourth could be it should comply anyway with the design standards. As imposed by the codes. Okay. So, therefore, the design optimization is in terms of member sizing, joint detailing, and to produce overall economic design. About the materials being used, and ease to fabrication. So, these are the factors based on which a structural design of an offshore platform is generally optimized. Okay. Now, let us talk about what would be the general design criteria or design acceptance criteria. Let us talk about the design acceptance criteria. Now, when you talk about design acceptance criteria, we have to refer to the codes of practice. Let us say with reference to AISC and APIRP codes. There are some basic criteria stipulated by these codes. Let us say the allowable stress shall be based on the code provisions. If you permit any increase in the basic allowable stress, it may be due to many reasons. It can be due to strain rate increase, it can be due to dynamic increase factor, etc. If you permit that in the design, it should be notified. Okay, that is very important. You must have to specify this very clearly in the design. So, that is one of the requirements of the design. Okay. Furthermore, the second condition of course comes is the slenderness ratio. The slenderness ratio K by R should follow the code accepted values for different members. We all know this is a standard procedure, we are not discussing that here. However, you must note that the slenderness ratio for compression members in form dominant designs, okay, cannot be more than 120. There is a limit. The third conditions come from the sizing, which is diameter to thickness ratio. The minimum diameter to thickness ratio for tubular members is 20. The maximum D by T ratio for tubular members is 60. However, under exceptional circumstances, you can increase this. Okay. The next condition, the design acceptance criteria is thickness limit of the member. There is a limit imposed on the thickness of the member. The primary members the beams, that is flexural members, cannot have a thickness lesser than 6 mm. If the member thickness exceeds 65 mm, then it is a special requirement. So, that is the upper limit we have. So, anywhere from 6 to 50 mm is the recommended thickness of the members. Furthermore, the chord thickness of the joints, because we are talking about tubular members, the chord thickness of the joints can be increased up to 65 millimeters or a D by T ratio of 20 if you have ring stiffness. The next condition comes as allowable deflection. Is one of the important serviceability criteria. The deflection should be limited to 1/200 or, to be very specific, of the span. The next condition is the fatigue life of the joint. The minimum fatigue life for the joints both accessible, inaccessible are different. For accessible joints, the minimum fatigue life is 60 years. For inaccessible joints, the minimum fatigue life should be 120 years. See, these are some thumb rules. These are some basic guidelines, design governance, which international codes commonly follow when we talk about large displacement structures in marine environment, where the environment influences the material degradation, and of course, it also causes special kinds of loads on structural systems, where steel is considered to be one of the most promising material for such kind of construction. Okay. Having said this, let us now get into the design methods. Before we enter into plastic design, we all know that analysis and design is a closed loop. Okay. The structural design generally is carried out to control the response of the structure under the combination of various loads. Analysis reflects the response behavior of a designed structure. Therefore, friends, it is a common understanding that analysis is carried out to check the adequacy of design. Structural design is more based on experience or understanding of the structural behavior under combination of various loads. But analysis is a sophisticated process which is computer aided to solve high end mathematical equations with the help of various numerical tools. The results of analysis, however, need to be checked with the designer to correlate this with the actual behavior of the structure. When we talk about strategic structures, structural design is more focused on arrangement of functional utilities to obtain a load balanced geometry. If we talk about design strategy of form dominant members, then we can say it is more focused on arrangement of functional utilities and the members. So, the objective is to obtain load balanced geometry. Okay, that is objective. So, the design should not be seen as sizing of the structural members. Okay. So, let us do not look design of form dominant systems as member sizing to encounter or to sustain the encountered loads. It is not simply the member sizing, it is a large picture in reality. The focus should be more towards the overall shape and size and geometric layout of the structure. So, the focus is towards the overall shape, size, layout of all utilities that locate or that form the part of the structure. So, if you talk about the top side of an offshore platform, then it is layout of various utilities. Let us quickly see what are various utilities of an offshore platform: drilling, processing, electrical, mechanical equipment, pipes, cranes and other lifting facilities, storage, housing or what we call as accommodation units, rescue units, helipad or helideck, etc. So, various utilities are first arranged. Based on that, a load balance geometry is obtained, that is actually the design. It is not member sizing, friends. Okay. So, we are looking design as much a larger perspective. So, the main objective of the design therefore is to minimize weight and maximize its functional ability. Okay. Therefore, friends, the functional design of a topside or any strategic structure preludes the structural design. So, ideal design philosophy maintains the equilibrium between the applied load and resistance that can offer by the structural system. Unlike in conventional design practices, where resistance is accounted only from the strength of the material, for strategic structures or form dominant designs, the resistance is also offered equally from the geometric form. So, even the geometric form, arrangement of members, their sizing, placement of heavy equipments, both vertical and horizontal zoning, spacing of critical operations such as lifting, loading, unloading, drilling plays a very important role in balancing the load acting on the structure. Okay? That is very important. So, various functional activities, their layout and their weight etc. also help in the design of form dominant structures. Example, top side of an offshore platform. Okay? The very examples we have seen in different kinds. Therefore, friends, a safe design is termed as resistance exceeding the load capacity. Okay? Resistance exceeds the load demand. Okay? As a resistance can also arise from geometric form, form dominance is carefully exploited to maintain the dynamic equilibrium between the resistance and the load. Okay? Therefore, it is important to ensure that the large displacement structures like form dominant systems maintain geometric stability while they are under activation of loads, because they undergo large deformation. These large deformation can get into a plastic deformation of the material. So, there should be one-to-one correspondence and support from the material to the structure and vice versa, so that the encountered loads are counteracted by the capacity of the form and of the material staying together. Okay? So, please note that the deformations being discussed here are not at the material level. We are also including them at the structural level. Okay? So, now there are different design methods which we all know, like working stress design, ultimate load design, limit state design, etc. Okay? Let us quickly look at an overall view of this before we get into the plastic design. So, in working stress design method, so let us say design methods, a comparison. Okay? This is only just to review what we already know. Most of you know this, but still for the completion's sake, let us review this quickly without spending much time and get into the plastic design. In working stress design, the demand at the working load is made to be lesser than the capacity of the material. Or capacity of the structure, let us put it like this. Okay. Now, the capacity of the structure comes from two. One comes from the geometry, which is static indeterminacy, redundancy we call. The other comes from the material. The one which comes from the material is stated as allowable stress limit. Okay. Usually this value is kept within the elastic limit of the material. So, we say sigma allowable usually is lesser than the elastic limit or stress at elastic limit of the material. That is a usual practice what we do in working stress design. Therefore, friends, the ratio of capacity of the material which is taken at the yield to the allowable stress is called as the factor of safety. So, this has got something called factor of safety, which is the ratio of the allowable stress to stress at yield. Okay, we do not take it till yield, we limit it below yield, and that is the factor of safety. So, the margin between the allowable stress and the working load is actually termed as a safety margin, right. So, there is an explicit safety margin in the design like this. Hence, in this design method, there are two tier safety margins. Okay. So, there are two tier safety margin. What are they? The first one is by limiting the stress to stress allowable, which is lesser than yield. So, there is a reserve capacity in terms of the material. Okay. The other one is the actual capacity of the material. Well, material also has reserve energy, na? So, these two together has two tier safety margin. So, one should carefully note that still the reserve capacity of the material is beyond its yield, which is completely ignored in the design procedure. Okay, let us put this mark here. The reserve capacity of the material beyond yield is completely ignored in this design procedure, correct. The second one, which is very common, is ultimate load design. In ultimate load design case, the ultimate load is computed by enhancing the demand at working load by a load factor. So, in this case what we do? We enhance or increase the demand at working load by a load factor. We all know, for example, the load factor of 1.5 is being recommended. Okay? But still the material strength is limited only to its yield value. Hence, the safety margin which was present in the working stress method remains unchanged, is it not? The safety margin present in the earlier design method remains unchanged, but the load has been increased from working load to ultimate load, right. So, what we did is we have increased the load from working to ultimate using a load factor, but the safety margin of the material is not changed. Therefore, the factor of safety is now replaced by load factor, is it not? However, you must understand that the reserve capacity of the material beyond yield is still unexploited. Even in this method, correct? In limit state design, procedure, the ultimate capacity of the material is also reduced by a partial safety factor. So, what we do is we reduce the ultimate capacity of the material using a partial safety factor for materials which is generally indicated as gamma m. On the contrast, the demand at the design load is enhanced. We call this as gamma f using a partial safety factor for loads which we discussed in detail. So, the material capacity is restricted only up to yield, okay, as in other methods. Therefore, let us quickly see this as a good graphical comparison on the screen. We will say that this is my 0 level and we say this is my working stress. Method. Okay. So, what we do from here is this is working stress value, okay, working stress value. So, let us say we try to increase or in working stress design, this becomes my load criteria or the strength criteria, whereas in limit state design the load at working load is enhanced, okay, is enhanced by gamma L, but the material is applied with gamma m, okay. So, this becomes my parameter for working stress design and this becomes my parameter for limit state design. If we talk about ultimate load design, what I do is I enhance the material characteristic further and take it till the top. Okay. So, in all the three cases, we can very well see the safety factor is inherited in the material level itself. Okay. However, the reserve energy possessed by steel is relatively higher and that is not used. Is not used, is it not? And it is relatively higher in steel, and that should be accounted in the design, is it not? So, if you look at the reserve energy, before we do, let us make a comparison. The working stress design does not permit or does not invoke even any damage. So, zero damage condition. The limit state design invokes nominal damage, but meets serviceability requirements. The ultimate load design invokes damage, but no collapse. So, safety of the geometry is ensured. So, if you look at the reserve energy possessed by structural steel, it is very amazing. Let us see this. Let us try to plot the stress strain curve of structural steel. So, the initial slope let it be same for all the types of reserve energies. So, initially this is for mild steel. I am just drawing qualitatively, let us say this is going up to 0.25. Okay. If you look at the high strength steel, okay, this is my mild steel. Oh, sorry. Mild steel. This is the energy we have. When you look at high strength steel, this is low carbon steel. Okay, and the limitation stops at about 0.2, and this becomes the energy. When you talk about special grade of steel which is heat treated, this is furthermore but stops at about, this is 0.15, this is 0.2, this is 0.1. So, this is heat treated construction alloy steel, which is quenched and tempered alloy steel. Okay, this reserve energy is still high. So, friends, one can very well see the design methods can be now divided into two major domains. can be divided into two major domains. One is force controlled, other is displacement controlled. In force control design method, failure occurs if the imposed load exceeds yield strength. So, in force control method, failure occurs if the load exceeds yield strength. But in displacement control method, no failure occurs even if the load exceeds yield displacement. Okay, please carefully understand this. Provided the material is ductile, however, damage occurs in excessive yielding and will cause permanent deformation. This is termed as plastic deformation. Okay. So, let us say what would be the concept of plastic design now based on this. So, the concept of plastic design is induced force can be more than yield strength. It will not cause damage, but causes plastic deformation, which is a permanent damage. Please understand that. So, in plastic design, you are enabling, you are permitting a permanent damage. But however, the force level will be much more than the yield strength of the material. Okay? Therefore, friends, material to be used in plastic design should possess high post elastic deformability. Steel has this property. Okay? So, let us look into this graphically. If we plot this as deformation and load curve, so we can have a nice curve and like this. Okay. Let us say at 1 you can have a load level which is load level 1, I call this P1, where no permanent deformation is caused. It is at this point which is level, I will call this as level 1, level 2, which has reached yield. The load can be still more than that, see here, the load can be still more than that, but during this increase in load you also encounter large permanent damage, okay, and of course it collapse. It will undergo a permanent damage or a failure, okay. Now if you look at the elastoplastic deformation of steel, I will draw it here itself, it is easy. Elastoplastic deformation of steel. Steel has got ideally a good yield plateau and then it goes, okay. So this is the yield plateau. Okay, the strain and stress, of course. So this is now going to be idealized in my plastic design as a bilinear curve where I am going to stop this at sigma y, okay. I am going to stop, and this is my epsilon y. So this is going to be my idealized curve which I am going to use for plastic design. This is for steel, okay, this is for steel. So steel has got good ductility, elastoplastic idealization which can be applicable to steel, and steel shows a very good yield plateau which suffices the design requirement of increase from P2 to P3 with permission of permanent damage as envisaged here. Of course, we are not entering into the region at all, okay. This region is not entered. We are limiting till here. So if I say this is my XX line, the XX line is here, okay. I am limiting till here. Okay friends, in this lecture, let us look at the summary what we learned. We learned various design methods quickly. We compared them and we understood something called factor of safety, gamma m and gamma f for load and material, and we realized that how the methods of design exploits the steel capacity reserve energy up to a level. Then we moved on to the plastic design which states that the design process controls the stress at yield but allows increase in imposed load at a cost of plastic deformation, which is a permanent damage in the member. Okay. So, if you want to allow this design to be incorporated, you have to have the material capability of ductility induced in the material, plus when the structures are undergoing large displacements because of the form dominance, it should be supported equally and parallelly by the material. Therefore, the material should be also remaining elastic, or elastoplastic conditions should be available in the material with enough ductility, so that the one-to-one relationship between the demand from the structure, expectation from the material matches each other to counteract the load acting on the structure without any failure. Okay. In all the time, remember friends, the geometric stability of the structure even under accidental worst scenario should be guaranteed. There is no design procedure which is acceptable by any courts of practice in the world which says that the geometric stability can be overtoppled at the cost of increase in load carrying capacity of the member or the material usage effectiveness. Okay friends. So, we will close it here for this lecture. We will continue in the next lecture. Thank you. Have a good day. Bye.